Alright, automatic control principles and practices. Chapter 5, frequency response. Frequency response method are cumbersome with the step function method that require special equipment and more time consuming. From a practical viewpoint, the justification of the allow of the division of the control loop of the tributary number of elements of the same frequency response curves on each of the elements to predict the behavior in the loop of the combination when any of the components of the frequency response is known. Frequency response is similar to step function response in that it compares the output component with a group of components with an input, similar also with the object of attaining stable control system maximum correction speed. The difference between the two form of the input signal, which is a sudden change in one case and continuous change signal in the other. Sinusoidal input. The pattern with the continuous changing signal follows is that of the sinusoidal curve are shown in Figure 5.1. Reason for choosing. Figure sinusoidal waves and minutes in displacement type A and T, the travel length, and your dips and curves A and B. Such signal mainly would allow the correlation of mathematical experimental result, however, the more academic than practical interest. There is, however, the deeper belief that choosing the continuous changing signal is maybe the physical system has the response for the simple sinusoidal pattern. Whenever the elastic force, restoring force is involved in the springs of the car, the pendulum of the clock of the mercury column and the manometer, etc., the system will tend to restore the balanced condition by sinusoidal motions once when the equilibrium is effective with the outside force. Periodic motion, sinusoidal pattern repeating itself with a definite interval times is called a simple harmonic motion. The amount of amplitude of the sinusoidal is defined with the distance of the mean with the value of the point of maximum displacement indicated by A in Figure 1 curve A. This time required with the motion to complete one cycle called the period. Thus in Figure 5.1, either curve A or B at a period of time of 12 minutes after the pattern repeats itself once a period, and the amplitude is known whether possible to draw with the sinusoidal curve with the help of the trigonometry table. It is simple by using the following values: 0 angle sin 0, 15, 259, 30, 500, 45, 707, 75, 966, 90, 100. The period of the time intervals is subdivided in 360 degrees. Figure 5.1 interval conceived within 12 minutes. Hence, each minute is equal to 30 degrees. The amplitude is multiplied with the sin value of the various points obtained with the displacement. And thus, particular points following the table is an establishing curve A of the Figure 5.1, which amplitude is equal to. Time intervals 1, 0, 5, and a halves. Angles in degrees 0, 15, 30, 45, 60, 75, and displacement angle is same as the angles sinusoidal curve values. Okay, that's enough points to establish the draw of the curve up to 90 degrees from the preceding table to be used up to 180 degrees by taking the value of the descending order 096, 086, 6707, etc. Successful intervals 0 half a minute. Obviously, even the negative values of the curve can be completed. Phase and log and frequency magnitude ratio. Figure 5.1 shows the two curves of the curve A and curve B, but then can be visualized with the input-output product of the gas heat of the steam generators above the gas fuel control valve were to be cycled according to the curve A. Then the steam pressure would follow with a similar pattern, only delayed in action. The delay is equal to 2 minutes of the Figure 5.1 delay is sinusoidal representative of the call of the phase lag or phase angle expressed in the degree of the previous established period. The time of the 12 minutes for the cave under consideration corresponds with 360 degrees. Hence the phase angle is 60 degrees where the minus signal indicates the output lags behind the input. With a period of 12 minutes, meaning with a complete cycle with a periodic motion is completed in this time interval. Conversely, with the means of the half and 1/12 of the cycle is completed in 1 minute. The frequency with the sinusoidal input expressed in those terms is half cycle a minute. Frequency with E of the curve of the Figure 5.1 the frequency is inverse of the period. The higher the frequency of the fuel valve, which means the faster move through the periodic motion, the more difficult becomes the pressure flow of the input. Although the frequency of both the input and output is always the same with the phase angle, with the increase of the amplitude of the pressure curve will get smaller. Finally, frequency reached with the two halves of the pressure flow will stay with the constant as same sum average value. Ratio between the amplitude and output signal amplitude input signal is called magnitude ratio. Technique of taking frequency response data. Suppose it's desired to take the frequency response with the steam generator control system. The control is assumed with the air operated with a proportional position action. Fuel is emitted by the generator, which produces the stream of the pressure, and the steam is measured with the control puts out when the signal is a function of the deviate of the steam pressure from a set point, with the control signal is implied to control the value, which regulates the fuel flow with the interaction closed loop, and is thus established. In order to obtain the frequency response, each system is necessary to open the loop, and in some arbitrary point between the controller valve is shown figure 5T with a closed loop, thus becoming an open loop. So you have the fuel valve, steam generator, steam going into this from steam to steam pressure controller to a sine wave generator, and that is open loop frequency. Input signal is applied with the control value with the required with the pneumatic sine wave generator with the boost control variable speed electrical motor with the rotation motor shaft with the converter with the same harmonic motion by means of cam linkage or slide with the pneumatic relay with the operator with the linkage thus provided with the air pressure of the cycle with its incisional by increasing supply with the pressure with the varying lever ratio of the amplitude of the signal can be changed with the frequency is regulated with the motor speed control. Arrangement is basically the same with the hydraulic mechanical sine wave of the generator with the where electrical signals can be even the number of sine wave generators are commercially available. Another piece of equipment is a recorder illustrated in figure 5.2 which records with the graphically input with the input-output of the open loop. The important of the recorder does not have the attenuation and phase shift of the input signal. The frequency response with the testing equipment that must be considerably above with the frequency applied with the test of the open loop. Frequently, oscilloscopes the other electronic equipment are used for this purpose. A certain amplitude is chosen for a frequency test for the purpose of it not be quite necessary to always know what the amplitude at which the response data were taken. Amplitude is limited by the speed of the component. For example, the valve movement of 1 inch in 5 seconds. Choosing the amplitude with the corresponding with the valve motion in 1 inch limits for the frequency less than 3 cycles a second. The speed of the knob of the frequency may become the limiting factor. The difference between the speed of the frequency response with the important one system with a rather slow file with the input signal with the attenuation small with enough amplitude system will respond satisfactory even at a high frequency. For the larger amplitudes, however, the slowness of the system becomes the control factor for the web with the speed of the high frequency response for the both required. It depends entirely on the application. Once the amplitude is shown with the number of runs taken and changing only with the frequency of the input signal, assume with the following with the unless over the state with the proportional band over the controller and such that low enough frequencies the magnitude ratio is 1 frequency that increases data log with the put in the graphic form. Graphic representation frequency data frequency response system coordinate with the variable the frequency magnitude ratio phase lag with the figure 5.1 illustrate with the magnitude of the range of the phase lag with the 1 speed specifically frequency namely 1/2 cycle per minute. This information does not suffice to draw with the conclusion about the behavior of the control system for the purpose of the density with the graphically represented with the change of the magnitude ratio phase lag at various frequencies. Several methods exist. The Nyquist diagram has been used for many years. The advantage of compiling all of the information in a single curve, but in general, they consider more difficult to interpret than so-called the Bode diagram, a method that conveys the same information as the Nyquist diagram, but in two separate diagrams. These American Society of Mechanical Engineers accept the Bode diagram as preferred standard with the presentation of frequency response data. The Nyquist diagram in control of the figure 5.2 with the total stroke with 2 inch for the control output signal with a range of the 12 psi cycle from the value of the amplitude is 0.2 an inch or 2/10 of an inch corresponding with the cycle with the 3 with the amplitude of 1.2 psi. Suppose a certain frequency for the control output signal respond with the input with the maximum amplitude with 9600 of the psi, magnitude ratio of the output input with 9600 over the 1 and 2/10 equals 0.8 tenths. Figure 5.3 represents the Nyquist drawing corresponding with the control system. Figure 5.2 with 100 cycles of a minute with the magnitude ratio between the output with the input over the 1. The length of the area or vector A in figure 5.3 is proportional to the magnitude ratio of the phase angle is 0. At 300ths of the second, 300ths of the cycle in a minute with a phase angle of negative 30 degrees, although the magnitude ratio remains the same. Vector B hence for the length of the vector A with the display with a negative 30 is indicated in figure 5.3. Alright, show the cycles per minute, and then it goes 0, 270, 180, 90 cycles per minute, and you have 100, 300, 500, 700, 1, and 300s, and 500 is a cycle a minute with a phase angle with a negative 50 for the magnitude of the ratio of the 9/10 for the express for the making factor for the corresponding short vectors D, E, and F. The increase for the negative 8 for the angle with the decrease for the magnitude ratio actual 7/10 for the cycle a minute with the magnitude ratio. The decreases of the 1600s for the psi an inch, which if too small a value, the enter for the on the pilot plot. By connecting the endpoint with the vector curve they obtain with which can be either the interpretation control system like with the criteria established the system will be stable as long as that negative 1 point on the horizontal axis of figure 5.3 is left as to the left of the curve. Figure 5.4 shows several curves to be obtained with a proportional position control system. Curve 1 is typical single capacitancy system. The curve 2 the two capacitancy system. Curve 3 represents the 3 capacitancy system. 3 systems are stable, although the curve 3 gets close to the negative 1, which indicates some oscillation will be unavoidable. In this case, the curves 4 and 5, however, the system also with 3 capacitancy with the definable unstable system for the negative 1 is no longer to the left of the curve. The number of the capacity proportional position control system can be read with the negative diagram dividing into 4 quadrants indicated with the numbers 1, 2, 3, and 4 in Roman numerals. Figure 5.4, curve 1 remains. And then you have this frequency curve, Nyquist diagram, various progress, 1, 2, and 3, and 4 in the quadrants, 0, 90, 80, 90, negative 90, negative 22, 70. First quadrant here, the representative of the single capacitancy system of the curve enter the second course of the 2 capacitancy system, and curve 3, 4, and 5 stand with the 3 capacitancy system since they enter the third quadrant. So you have there 3 and 4 and 5 in the third, 1 in the first, and second in the second. The bow diagram, figure 5.5, give you the information figure 5.3, but put in form of the bow diagram of the upper curve, it illustrates the train with the magnitude ratio with the increased frequency scale, you the non-linear, the so-called logarithmic scale with the distance from the negative 100 to 110 is the same as the distance of the 110 to 1. Some of the step of the figures 2 tenths to the 4 tenths of the, or to 0, 6 tenths to 0, 8 tenths. Progressively shorter, thus the scale with the increasing value with the advantage of the lower value, the easier to read with the higher one has the further advantage of replacing the multiplication frequency response data with graphic conditions discussed later. In the lower diagram, phase angle is shown with a linear scale, while the logarithmic scale continues to be even as for frequencies. Phase lag and phase reversal. Figure 5.2 illustrates the method of taking the two simultaneously graph with the frequency response test as long as the output does not lag behind with the input with the corresponding graph would appear on the figure 5.6, where one of the mirror image of the other with the amplitude's input with the output signals are equal. The output is at the maximum when the input is at a minimum. Vice versa, since the full period corresponds to 360 with the distance between the maximum and minimum of the sinusoidal curve is 180 with the output is said with the lag behind in an input with the 1 by 180 degrees. You have the maximum ratio from 0 100 to 1, and your phase angle also 0 100 to 1 on your cycles per minute and phase angle. Actually, but this is not a phase lag with a phase reversal. Inherently, control action the controller has the counteract with the disturbance in the loop. For example, the increase in steam pressure may result in such of the action of the controller as to reduce the steam pressure. This is equivalent to saying 180 degrees phase reversal. Illustrating figures 5.6 is required with the graphic representation. Frequency response phase reversal is ignored. Only additional phase shift is represented in phase lag. So this shows input and output response curves on the graph. Stability conditions above there's additional phase shift of 180 degrees while the magnitude ratio is still unity. In this case, the maximum output with the coincide with the maximum input. The controller actually repeats the disturbance of staying with it instead of the counteracting system is unstable. The condition of the unity of magnitude ratio 100 degree phase angle must lag must therefore be avoided. Common practice except safety margins according to the following rules. One phase lag should be no more than 150 degrees for the magnitude ratio of the 1 or more of the 30 degree difference between the acceptable and the unstable conditions called phase margin. 2. For the degree of the phase lag magnitude ratio should be equal to less than 1/2. The magnitude ratio of 1/2 would be necessary to increase the factor of the two order when the making the unity with the hence make system unstable. The factor of which maybe the magnitude ratio has to be increased and obtain instability called the gain margin. Gain margin of 2 is therefore desirable for the process control. Acting according to the stability criteria with the result of obtaining the fastest practical control response under the stable condition. Figure 5.7 shows the frequency response curve will fulfill these conditions. The phase margin is 30 degrees, and the gain margin is 2. So you have the magnitude ratio, and that shows 1 and 1/2, and then that goes from 0 to 10 to 10, and phase margin root and gain margin rule. Phase margin rule, phase gain margin rule, 150, negative 150, 108 phase angle, cycles per minute. Alright, dead time instability factor. It can be concluded with the foregoing that increased phase angle without simultaneous decrease of the magnitude ratio will leave the instability expecting the case where the magnitude ratio is sufficiently below the unity of all of the condition and the creep of the phase angle with the concept of the magnitude result with the dead time such for the representation of the time to take with before changing in the loop becomes noticeable with the figure 5a illustrates the frequency response as a result from the dead time into the system and the response indicates its instability. Shows magnitude ratio 0 to 10 to 10. Your phase angle 0 to 90 to negative 180 cycles per second and 100 to 1. Combination of frequency response data. Frequency response of the control of any particular component is of the interest only with the frequency response of all of the other component of the control loop is equally known. It is possible to combine with these data to obtain the complete interpretation of the behavior of the control system. Block diagrams. Block diagrams illustrate how the frequency response of the component of the control loop with the combined with the figure 5 known show the typical application for the method of the pressure control system. The pressure is applied to the diaphragm spring with a combination with an example of the pressure and keep the jet pipe with the deflect to the right with the deflection with the proportional to the process of the pressure change. Oil is pumped through the jet pipe and leaves it up to the tip that to be directed with the two orifices which connect with the two sides of the actuating piston. As the jet pipe is deflect with the toe over the right, the more oil passes through the right hand into the left hand orifice. The piston moves over the left opening with a control valve, thereby reducing the pressure on the process line. When the block diagram control system is divided into the most obvious part of the quite arbitrary, the different breakdowns are position possible. Their system is not represented by blocks, normally process for the diaphragm spring combination jet pipe piston valve. Alright, so the process for the actuating piston going into the processing tube and then diaphragm out to the jet pipe and spring oil flow. Or you start it in process of PSI inches, PSI going to diaphragm spring and PSI jet pipe cubic inches in PSI, and then back to the cubic inches and seconds to piston inches and seconds over the cubic inches and seconds to inches and seconds over the valve in and over the end to input in seconds into the loop open. Or the process change with the pressure of the per inch of the valve motion with the linear with the relation of the stream with throughout with the hints of the process of the block read with the PSI in inches. The valve motion expressed in inches shown with the input with the pressure of the PSI as output with the pressure directed to over the diaphragm spring combination for the deflection with the impinge and inches and PSI pressure change. This is converted into cubic inches per second over the hydraulic flow with the beginning of the jet pipe with the piston transformed with the hydraulic flow into inches a second and the piston motion. Valve moves from within the piston with the final outcome in inches in a second. The important point of the chain with the malfunction has been performed each block under the loop, namely where the process is equal to inches times PSI and inches equal to PSI. Diaphragm spring is equal to PSI times inches over PSI, and then you get inches, etc. Each block acts as a multiplier upon its input. Each input is output with another block. This is possible to lump another to get lump to more of the blocks in input into one or simple multiplication. For example, the diaphragm spring block that can be combined with the jet pipe block given with the new block dimension inches over the PSI is equal to cubic inches. Inches over PSI times cubic inches over a second and divided by inches equal to cubic inches divided by second over PSI, which is obviously in line with the input with the PSI output with the cubic inches and second with the multiplying with a new block with the input result of the output. Each block has separately submitted with the frequency response test. For example, the process can be analyzed cycling with a valve with a measuring pressure, letting output to input both the magnitude ratio phase lag could always be obtained. Similar data could be obtained from each block. The output-input ratio with the magnitude ratio can be multiplied with obtaining with the overall magnitude ratio since the representation exactly with the relationship represented with the block diagram. The phase angle, however, must be added since they present delays in each block with similarly add up the single phase through the loop. Graphic addition of the frequency response data. Magnitude ratio of the frequency response data represented with the logarithmic scale with the resemble the slide rule scale with adding with the two distance calibrated with the magnitude factor, the equivalent to the multiplication. The result with the Bode diagram allowed with the graphic addition of magnitude ratio. Single phase angles represented with the linear scale with the graphic addition with the corresponding with the physical addition and with the required with the phase angle addition with the magnitude ratio phase angle with the illustrated in figure 510. With frequency response with the data with the components of the A and B with the combined with the result with the combination corresponding with the C. In order to graphically the magnitude of the ratio being 1 over the ratio of the 1 is u with the reference line with the obvious for the 1 considered the output of the equal to input with the ratio equals 1. There's no matter how many of the components are connected together, the output with the input ratio will still be equal 1 with the obvious for the because of the multiplication 1 does not change with the multiplicated. The illustration shows the three different arrows of the A, D, and G with which have been added with the two B, E, and H respectively. For example, the arrows A, B, and which have taken the same frequency, equal length with the opposite of the polarity. They have canceled each other with expression C by the point with a minor C by located with the unity magnitude ratio with the adding D and E with the opposite of the polarity have given and taken into account. Therefore, the result in F corresponds to the diminished by the D with the arrow I is as simply sum of the G and H both being equal polarity. Remember the additional result with the magnitude ratio C with the corresponding with the combined characteristic with the combination components A and B. The addition of phase angle shown in figure 510 uses 0 degrees phase angle as a reference, and when A lags by 110 degrees a certain frequency, B leads by 6 degrees of the same frequency, and the combined phase angle with negative 50 degrees illustrated addition of the baseline in this method. Alright, so here we have the frequency and magnitude ratio 0, 10 to 100, and that's A, and then B, and then C, and then A, B, and C. Unstable components of the stable loop. It's interesting to observe the component A, figure 510, is unstable to the phase angle with a negative 180 degree frequency, which the magnitude ratio is equal to unity B by adding B and A with the result in C with the combined with the response shows stability of the proof that the stable control loop may contain the components considered by themselves unstable. Alright, proportional speed floating control. Figure 511 shows the response with the proportional speed floating control whether it's along with the input signal supplied with the output, such for the control with the continues changes a certain speed when the change of the input signal is slow with the floating speed with the control within the amplitude of the output becomes larger with the input, hence with the slow with the frequency, signal with the greater the magnitude ratio. Once again, cycle over minutes in phase and magnitude ratio A and B. The output of the proportional speed floating control in reverse direction with the input signal will pass through the air with equivalent to the phase lag with a 90 degree with the count with the same phase angle within is shown in figure 511. Two graphs A and B shown with the illustration of the magnitude of the ratio correspond with the different flow rates of the control of the magnitude ratio with a given frequency is directly proportional to the flow rate. For example, the graph B corresponds with the flowing rate with a 10 times greater than the graph A with the phase angle remains unaffected. Process without self-regulation becomes essentially with like of the proportional speed floating control. For example, the water in the tank with the control constant flow of leaving the tank will continue to change within one direction from the given flow, and when the tank the phase lag would be likely 90 degrees. If the process without self-regulation combined with the proportional speed floating control of the phase lag with a combination with the 90 plus 90 equals 180 degrees. Some of the point with the frequency response with the curve of the magnitude ratio will be 1, hence the unstable combination of the proportional speed floating controller cannot be used for the process without self-regulation. 512 shows the illustrates the action proportional speed floating controller with the control loop. In this case, the loop is considered to be consist of only controller process graphs A and C, or the controller response graph M, process of the response graph A and D are the control loop response process with the controller combined initially with the flowing rate with the control with the set forth of condition A with the response. Control loop B represents the combining of the frequency response on the process. So here we have a controller process, and then there's capacity, and then a controller process and control loop on these. Magnitude ratio 0, 10 to 10. Phase angles 0, 60, 0, negative 60, 120, 80, 180, 220, 1/10 of a cycle over 1 per minute, 1 full minute. Phase angle graph E, sum of the phase angle with the process with the control of approximately 17 hundredths of a cycle with a minute, and the phase angle is negative 150 degrees. Comparison of the magnitude ratio curve shows that it is possible to compute the floating rate with the control will consider the still remain within of the stability. Graphic C with the response with the floating rate about 10 times the A with the new control loop pressure. Response with the illustration of the graph D with the response with the magnitude of the 1 to 0 at 7 hundredths for the cycle of a minute at the frequency of the will of phase angle with the 158 degrees, negative 150 degrees, and negative 180 degrees with the magnitude ratio of the 1/2. Stability thus is still assured with the speed of the response with the controller is improved considerably. Proportional position control. With the frequency response with the curve of the proportional position control that would be a straight line both with the magnitude ratio and the phase angle with a relatively high frequency illustrated in figure 513. Magnitude ratio 1/10 of the 10, A and B. Phase angle 0, 30, negative 60, negative 90, 1 cycle to 1,000 cycles per minute. Principle of the proportional position action implied with the change of the input signal to reflect with the immediate output signal with the proportional magnitude. However, when the input signal changes very rapidly, the output signal can no longer follow the actuation of the signal, as will the delay of the curve of the produce of the degree of the magnitude ratio and curve of the phase lag. Graph of the B correspond with the magnitude ratio 10 times that of A. This produces the change of the proportional band. Nearing the proportional band of the controller will intend for the increase of the magnitude ratio by 10 when the phase lag is not altered. Figure 5.14 respond to the control loop contained with the proportional position control of the process for the dead time only. With the graph A, show the magnitude of A and B going straight from and then phase angle slightly down. Represent unstable conditions with the 180 degrees phase over the magnitude of the ratio of 1/2 or not 1/2 or less. Dead time cannot be eliminated, necessary to increase the proportional band. Suppose the initial magnitude ratio of the 1, profit the control of the respect with the combined ratio of the 1, double the proportional band, result of the magnitude of 1/2 of the both of the control of the control loop correspond with the B in the figure 5.14 and assuring stability. Widening with the proportional band, result of the slower control of the response with the compromised and control system required with the greater stability of equivalent slower corrective action. Stability, steady state of condition with the corresponding with the frequency signal approach to zero cycle with its called steady state with the equivalent control system the re-establish of the balance condition after a disturbance. Magnitude ratio proportional position control is sufficient low frequency at 1 or with 0 phase angle with the implied with the 0 input and output will also be 0. Offset characteristics. Offset inherent steady state with the characteristics of the proportional position control that cannot be overcome because of the output input of the ratio of the proportional position control that does not increase the steady state, but hence does not no additional impedance that can be expected. This is the difference between proportional speed flowing with the controller which show with the increase of the magnitude ratio of the system approach the steady state condition comparison figure 5.11 and 5.13. Illustrate the difference between two control actions. One graph with a negative slope, the other is zero slope. Proportional position action compared with the proportional speed floating action offers the advantage provided with the inherently stable component with the permitting operation with the larger magnitude ratios. This increases the speed of response. Combination of the proportional speed floating proportional position action proportional plus the reset control becomes therefore the desirable since this gives facts action eliminates offset with the proportional plus reset recontroller. Figure 5.15 respond with the proportional plus reset with the control of the reset rate of the controller expressed by so-called with the break with the frequency of the illustrated with the dash line. Figure 5.15 both slanted line correspond with the reset action with the horizontal line with the correspond with the proportional position action with the pro line with the straight line frequency in which for the two line with the intersect with the break frequency phase lag is 45 degrees with the break frequency with the ratio basic reset with the ratio with the obtained multiplying with the break frequency by 2 by pi or 600.6.28. That means the break frequency I reset rate speed per minute is and frequency is in cycles over a minute. Thus, figure 5.15 graph A break frequency is 1/10, and hence the reset is 6.28 times 1/10 over the 628,000 repeats a minute. When the reset rates attain with the angle of the wind slatted line forms, and they show the magnitude ratios 1 to 10, A, B, and C. Phase angles A equal to C and B in cycles per minute going from 0 to 110, 0 to 1. Horizontal line with the remains unchanged with the slope of the line always expressed with the degree of the magnitude ratio of the roughly 9/10 of the increase of the frequency of the 10-time magnitude ratio. Graph of A should be shifted to either horizontal or vertical plane. Shifting the horizontal plane means changing the reset rate. For example, the graph B with the result of the increase of the reset with the ratio of the 1 1/4 repeats in a minute. It was similar with a narrow proportional band with the 1/4 increase of the magnitude ratio 4 times. Horizontal shift. Graph A is obtained with graph C. Result of the phase angle is unaffected by the change of the proportional band, but shift of the reset rates is adjusted to have some effect for the final adjustment of the controller. This, however, is little practical consequent with the illustrated with the following example can easily be ignored. Adjustment of the proportional plus reset controller is previous chapter with described how reset action of the proportional plus reset controller can be adjusted by using a relation, and that is the reset rate is equal to 1.2 over time, or the reset ratio in time is between the two successful maximum oscillation critical setting. Critical setting was defined with the widest proportional band, which continues oscillation occurs with the corresponding magnitude ratio of the 1 phase lag of 180 degrees time. The T is equal to is the period inverse of the frequency of that condition on the basis of the possible determinant of the controller adjustment from frequency to respond to the data with the control loop of the data should be taken from the reset action omitted with the result of the figure 5.16 where the magnitude response to ratio is 2 for the frequency up to 1/400th of the cycle in a minute in order to the magnitude ratio and the phase over the angle 0, 60, 120, 240, and negatives 100,000 to 1 cycles per minute. Determine the proportional band frequency and phase angle over the negative 150 degrees of determined in this case with the 2700ths of the cycle per minute within accordance with the rule 1 stability conditions. Thus, the graph magnitude ratio shift the vertical plane with the ratio of the 1 to coincide with the frequency, the dash line with the corresponding with the condition. It would be found with the new amplitude ratio with the 4 times with the world 1 over the aim of the frequency mean with the controller sensitivity can be increased by a factor of the 4 with equivalent reducing the proportional band at 1/4% value. So from the reset rate with the necessary to determine the frequency with the at lag 180 degree phase angle with the resonant with the case of the 4/10 of the cycle of the minutes of the period with the inversely frequency with the corresponding with the period of 2.5 minutes. Reset rate then is equal to the reset rate is 1.2 over 2.5 would give you 400 over repeats in a minute. Figure 517 illustrates the chain with the control loop response due to the addition of the reset action with the condition dash line. Figure 516 combined with the added reset with the phase angle with the representing the 3 graphs. 1, A, the response without reset action. B, the phase angle due to the proportional reset action. C, with the result of the combination of those. C, with the graph that differs considerably from the original A graph, but show the phase lag with the 150 degrees at practical same frequency. Hence, the stability condition remains unaltered. Proportional plus reset plus rate controller. In addition to the rate action with the provided with the corrective action proportion of the speed with the control variable deviates with the set with the point you with the compensate with the large time constant and process only the measuring elements of the effect with the rate with the action with the proportional speed with the deviation must have the increased effect with the frequency of the test signal. Figure 518 show with the frequency response with the proportional plus for the reset with the plus of the rate controller. Increased magnitude ratio after with the 3/10 of the cycle with a minute with the due with the rate action graph with the 2 break frequency with the 1/8 or 800ths of the cycle in a minute or other than 4/10 of the cycle from the first break with the frequency reset rate with the determined previously described. In the cases, half of the repeats in a minute with the rate it can be determined by the equality of D. The rate of time in a minute is equal to 1 over 2 times pi times the frequency in cycles in a minute, or D is equal to 0/16 of the frequency. Thus presents this case. D is equal to 0.1600 over 4/10 for the equal to 4/10 of a minute. Slope of which stands slanted, line formed with the horizontal, same with whatever the rate is with the time magnitude, same with the slope of the reset action, only positive instead of the negative. Increasing, for example, the rate of 8/10 of the minute and the shift of the right hand with a slam with the proportion with the graph of the left, so the break frequency of the 2/10 of cycle in a minute is obtained, and show the magnitude ratio, and then A, B, and C cycles per minute over the phase angle with the 0, 120, 180, and 240. By changing the proportional band of the entire graph that shifted in the vertical plane, for example, the cutting of the proportional band in half of the graph that shifted to become the graph A with the phase angle that becomes modified with the added rate under the output signal, leave the input signal, the frequencies under the influence of the rate action. Figure 518 start with at 2/10 of the cycle in a minute. Adjustment proportional plus the reset plus rate controller. In a previous chapter, we discovered the adjustment of the base for the step function response with the point of the proportional band should be twice optical setting with the proportional position controllers with or without reset. The dimension of the proportional band could be narrowed with 1.7 times instead of twice at the critical setting when the rate of the action is added with the speed with the magnitude ratio could be increased because of the rate of the action. The reason with the effect of the phase shift has become noticeable as will be shown further below. With the same reason adjusting of the frequency response. Figure 519 magnitude ratio with 1 no longer refers to the phase angle of the 150 with but 1 over the negative 160. With figure 519 show with the graph with the same frequency runs. Response figure 516 reach of the rate of the action cut off with the adjustment of the response with the figure 519 minimum proportional band stable the condition the result of the dash line with the B with the magnitude ratio of the 1 is at negative 160 with the degree with the low frequency with the edge is at 10 instead of 2 with the where with the 5 times initial ratio with the 210 with the times initial proportional band to determine the reset rate of action corresponding with the express for the provision of the chapter would be I equals 2 over the time, or D equals time over 8. I is the reset rate of the read per minutes, D is the rate of times in minutes, and then T is the period of the minutes referred to the critical setting 2 with the 100 degree phase angle with the present with the period with the negative 180 degree with the 2.5 minutes. Hence the reset with the 8.10ths of the minute repeats in a minute, the rate over the 3100ths a minute. Adjust the reset rate and actions accordingly with the repeat the frequency response with the tap of the control loop, result of the paragraph C, figure 519, both the magnitude ratio and phase angle with a phase angle with a graph of the resulting adding Thras's phase angle A2 with the control of the phase angle D. It can be seen in the frequency at which the curve A showed at 160 degrees of the phase angle now shows only at 150 degree, but the justified initial assumption of the 160 degrees in this case of the rate of action instead of the conventional 150 degrees. Alright, in conclusion, the proceeding with the description illustrated with the graph of the word more with the less of the ideal eye, but the actual reading frequently should be considered with a random variation with a smooth curve only with the indicator with the trend with the in view with those conditions differential between 150 and 160 degrees may become impractical. The question arrived at the accuracy of the method with the points with the limitation frequency rather the data response data with the either the setting of the automatic control of the system when they actually install with the step of the function respond with the method similar and more reliable frequency response method with the advantage of remaining frequency response data allowed with the theoretical combination of several components without being installed with the estimation of the approximate magnitude of the setting will be. Chapter 6, Mechanical Components.